Sound is an amazing phenomenon that we experience every day from all types of sources, whether it's from the crashing of a construction site, the whizzing of a car, or the simple ruffling of leaves. There are also more particular sounds that we are able to code meaning into. For example, the meow of a cat, the bird call of the putu, and human conversations. Other sounds can be particular in the sense that they have specific pitches that we arrange into melodies or chords, which is considered the foundation of music, although John Cage might think otherwise.
Hey, yeah.
Regardless, sound is also part of the study of physics and is associated with waves. In physics, there are many types of waves we can talk about, but because we are on the topic of sound, we will be discussing mechanical waves. The physics definition for a wave is a disturbance propagating energy through space. Thinking about waves, the first thing you might think about are the waves on the surface of water. When you watch a wave move across the smooth surface of a pond, there's a recognizable velocity of that wave. However, the entire pond is not moving with it. Rather, the water is moving up and down as the wave passes through the water. The wave oscillates through a medium without carrying the matter of the medium along with it. Sound waves are similar to those water waves because it travels through a medium, like air or water.
However, there is a difference. Mechanical waves that travel on the surface of the water is what we call transverse waves, which means that the medium in which the wave is traveling through is oscillating perpendicular to the direction that the wave is moving. So you can draw a 90-degree angle between the movement of the particle and the direction in which the wave is moving. Sound waves, on the other hand, are what we call longitudinal waves, and it's when the back and forth of the medium is moving in parallel to the direction in which the wave is moving. It looks something like this.
As you can see, there are parts of the slinky where the loops are bunched together and other parts that they are spread apart. The areas that are bunched up are called compression zones, while the areas that are spread apart are called rarefaction zones. The distance between two separate compression zones or two separate rarefaction zones is called the wavelength and is given by the symbol lambda. Now, confusion might arise because on sound editing platforms like Ableton, Audacity, Logic Pro, sound waves are represented to look like transverse waves. This is when we have to reflect on graphical representation.
So take a look at this graph on the top. If we imagine that we have a special camera that can take pictures of air pressure of a given space with different intervals of time, then we can imagine that the x-axis is time. Then over time, in a given spot, there are places where the compression zone will pass, and then over time, a rarefaction zone will pass. We can represent this with the graph below. Notice how the crest of the sine wave is where the compression zone is, and the troughs are where the rarefaction zones are. This is because the y-axis is air pressure. That means that the middle line for this graph is kind of like the representation of the air pressure when there is silence, or something close.
Now, there are two types of graphs we can represent longitudinal waves with. What we just saw was air pressure over time. However, the x-axis can also be displacement. With longitudinal waves, we can label the vertical axis as air pressure or density of air molecules. on the time graph at the bottom, we can see that the time between two crests is a time period and is associated with the time it takes for two compression zones to pass a given point. Another way of thinking about this idea is to think of a cycle as an entire wavelength passing a given point. Then the time period is the time it takes to complete a cycle. There is a formula that relates frequency to time period, which is frequency equals 1 over the time period. So frequency is like the number of times a cycle passes per second. As we can see, the wavelength and frequency are very closely related. If we think of wavelength as distance and frequency as rate, it sounds familiar to the definition of velocity, which is the rate of change of displacement. Consequentially, there is an equation for that. That is, speed of sound equals wavelength times frequency. Notice how there aren't any arrows above the variables in the second equation. This is because we've decided to simplify things by making the speed of sound a scalar quantity.
Now that we've established what a sound wave looks like, how we can represent it on a graph, and the basics of music, it's time for a jam session. Ready?
Ready.
This instrument is a jar with water in it, and it changes pitch. How do we explain that? We will need ideas from both kinematics and wave theory.
Looking at the joblar, we can see that when more water is tilted on the lid, the pitch or the frequency is lower. Given the speed of sound is the same in the air, this means that the wavelength must be larger. This is when Newton's laws and kinematics comes into play. Assuming that I am hitting the surface of the lid with the same force, when the mass of the lid increases, then the acceleration will be lower. Therefore, the maximum velocity that the jar reaches is lower than when there is less force acting on the jar. Even though the velocity of the jar of the lid has changed, because sound wave velocity is dependent on the medium, what is affected is the wavelength and frequency. In other words, because the jar lid is moving slower, it takes longer to move from one extreme to the other. So the time it takes to complete a cycle is slower. So the wavelength is longer and the frequency is lower.